Okay, so good morning and welcome to this joint class of medical robotics and robotics 2. So the topic of today is visual servoing, which is a methodology that can be used for controlling robotic systems with different structure and in different application domains. So the medical domain is one of these, and this is the reason why we study this topic in medical robotics. So today we will study the fundamentals of this methodology, that is the mathematical foundation of this. And in the next lecture, we will see all the application and also how this paradigm declines to the application in the medical domain. Okay, so as the name suggests, visual servoing uses information acquired by vision sensors for controlling robots, as said. So vision sensors in this lecture will be mainly camera, actually monocular cameras, but they can be of different technological, can be, technologically very different. In fact, in the next lecture, we will see that this vision sensor will be the imaging systems, the medical imaging systems like ultrasounds or computerized tomography or magnetic resonance imaging devices. Okay, so why is this is which are the benefits of using this kind of using information provided by a vision sensor? Well, this is the information provided by a camera in particular is very rich. So is what we get through our eyes, and this is at the same time an advantage and also a drawback, because the being the information so rich is also complex, and then to find out what we really need to control, to achieve, to execute a task, sometimes is difficult. So it requires some degree of pre-formalization of the problem and modeling of the problem to find out which are the essential information that we need. Here we see, as said before, can be applied, is a methodology that can be applied in very different domains. And so in this slide, we see what we can achieve using the visual servoing methodology. For example, here we see it applied in the serial harvesting, in a serial harvesting application, and the idea is that by using a camera, the vehicle that you see in the video, and you will see now in a while, can follow the boundary between the part of the field that has been already covered and the part that has to be covered, so as to obtain an optimal coverage of the whole field. Here instead we see an application to autonomous driving of vehicles. This is of course an application that today is very familiar and popular, and what we see here is how this vehicle autonomously moves to track this target that is held by a human. Of course, this is a proof of concept of what can be achieved using this visual servoing technique. So you see that the human operator moves here. There is a visual target, most probably is a very simple one that here we can see, but this car moves in such a way to maintain a given distance between the target and the camera, of course, that is mounted on the vehicle, and that's between the target and the camera. Here we, and in these two applications, we have seen visual servo. I mean, the robot is a mobile base, essentially, and the camera moves rigidly with the vehicle, with the robot itself. Here we see a different application. I mean, different, slightly different. Of course, the principle is the same, but this is closer to fixed base manipulator. Here we see that the camera is mounted on a pan tilt mechanism that can be thought as like a 2 degrees of freedom manipulator, and the camera moves so you see the motion of the camera, it moves so as to keep this person at the center of the field of view of the camera itself, of the image plane. This is the application, I mean, is in the surveillance can be find this kind of this example is an example of application in for surveillance purposes. And here we also have one of the first examples of application of visual servoing in the medical domain. So what you see here, here there is a pig, and this is the heart of a pig that is on which some visible features have been mounted. And we will see what feature means in a while. And then by tracking these features using the visual servoing technique, you see that the robot synchronizes with the motion of the heart, of the heart beating, so as to obtain. The idea is to, on one side, to provide, to display at the operator's side, at the doctor's side, a steady image, but this is also done, and we will see this particularly in the, during the next lecture. This is also done to keep a constant distance between the surgical camera, endoscopic camera, and the organ that is moving inside the body. And this is also used to track the motion of the surgical instrument inside the body. Okay, we will see this in deep during the next lecture, but this slide was to provide you an idea of how wide is the field, the range of applications for this general control methodology. Now, of course, as said before, this methodology uses visual information, and the visual information, as said, is very rich, but at the same time is complex. And then to find the information that we actually need to perform a given task, we need to process the image. So there are some operations that need to be done to use this information for controlling the robot. First of all, this information need to be extracted in real time, because we are talking about, of course, real-time control. And usually, in the image, we look for some features of interest. Simple features of interest can be points in the image. In the last example that we have seen, there were 4 points that were visible in the image, and those were exactly the image features used to synchronize the robot with the bidding art. Also, in the very first application here that we have seen at some point, there is a line that the feature that is used by the visual servoing algorithm to move along the boundary of covered and not yet covered field, and so on. So the features can be, complicated at will. We will see that there is something, they cannot be arbitrarily complex, because in the end, what we will look for in providing the mathematical model for to find out the control law based on this visual information, we need to relate the motion of these features to the motion of the robot analytically. So, in finding out these features, we need to compute some metrics, as we will see after, that is called the interaction matrix, that does exactly this. So, we'll see. Now, this is the finding out the features is a part of the challenges in visual servoing control algorithm. Now, but once we have decided which features are we looking for, or which features our control algorithm relies, we need to extract these features from images. Then we need some low-level processing of the images. Low-level processes that goes from binarization of the image to segmentation and labeling, and so segmentation of the image with some semantics associated to the region of our segmentation, and interpretation, so goes from the low level, just a thresholding, for example, operation that distinguishes pixels whose intensity is above some threshold from those that are below, have an intensity below the given threshold, until the interpretation of this region, these features that we have found in the images. And so, for example, associating some characteristic parameters to a group of pixels, to a segment, to a region in the image that we have found out with lower level processing procedures, until the problem of finding the correspondences between points and characteristics of objects in different images. Why we want to find these characteristics? First of all, when the object is moving and we want to track this object, then we need to find these correspondences. And if we are looking at the same scene from two different points of view, so the so-called stereo vision, then we need to know on the respective image plane which pixels actually refer to the same object in the 3D space. So we need, this is a problem of finding the correspondences between pixels. So the problem of image processing, I think you studied this in the vision and perception course. It is not the subject of this lecture, but indeed the visual servoing paradigm relies on an efficient, also efficient image processing technique, because as said, this should be a real-time step in the visual servoing control scheme. Okay, so the once again, remember that what we will try today, what we will do today will be to link the motion of some features on the image to the motion of the manipulator. To do this, as said, we need to, first of all, to find out this feature, so elaborate the image, process the image information. But the motion of features with respect to the robot, and so or the relationship between these two motions depend also on the configuration of the visual system and on the setup of the camera with respect to the robot. So first of all, so let's list here. Let's remember which are possible configurations of a vision system. So we can have 1, 2, or more cameras. Today we will see the example of one camera, but the methodology, the paradigm, the control paradigm generalizes to more cameras. This could be, of course, gray level or color cameras. We can have 3D stereo vision systems. We could have real stereo vision system, or also we could emulate stereo vision systems by moving the camera. Okay, and then look at the same object from different point of view. As said, also the camera positioning with respect to the system that we want to control, of course, has an influence on this mapping between velocity of the features and motion of the robot. So we will see in particular two camera positioning modality. One that is that says the camera in a fixed position, another one in which the camera moves with the robot, so it is mounted on the manipulator or on a car, as we have seen in the previous examples. We can also have some internal degrees of freedom, like the camera is mounted either on the end effector or of a manipulator, but this end effector could also be, for example, the head of a humanoid robot, could be a manipulator mounted on a mobile base. So as said before, the robotic system can have a very different structure. Okay, so the camera positioning. The camera positioning, said, can be in a fixed, the camera can be in a fixed position, like in this example. So this is the camera. This is the target that we want to observe, with respect to which we want to control the manipulator, and this is the image plane. Okay, so if this object, clearly visible from the camera, because it's like the feature here, imagine, is this small circle. If this circle moves to the right, what the camera will see is exactly the circle moving to the right. In the high in-end configuration, where the camera is in the end of the robot, okay, so mounted on the end effector of the manipulator, and here is the target. If the camera moves to the right, then the target in the image will move to the left. Okay, and so of course this changes the mapping of the between manipulator velocities and feature velocity in the image space, which is what we will be looking for. Here we see two examples of application of visual servoing for assembly. So here we have an high-end configuration. There is a camera mounted on the end effector of the manipulator. So the camera finds out the correct place for this part. So it's a proof of concept of an assembly system. And then based on the localization of this position, then the command, a control is computed for the manipulator. The final part, since the camera, as you can see, is mounted on the side of the gripper, used to move the parts correctly in their place. So the last part, because of this offset, is blind, and so it is for this reason that there is a hybrid force vision control, because in the last part, to exactly fit the piece in its place, some control of the interaction forces is used. But the power of this control paradigm is clearly shown here when we see that okay, so this is not an assembly of a part that is moved from one position to another position, of which we know the shapes and possibly also the position on the plane. No, here we see how the manipulator is able to track, to move. If the target is moved, the manipulator moves so as to track it and then find out finally the correct position where to place the part. Okay. Okay. Another here we are classifying, okay, the not only the camera, the setup of the system with respect to camera position, relative camera robot position, but then based on this and say independently on how we position the camera with respect to the robot, based on the visual information, we can then design different control scheme. We can adopt different control scheme. This depends also on our, the level at which we can access the robot control. Okay, so here we see a typical control scheme that is an indirect or external visual servoing control scheme, in which, here is the robot. On the end effector of the robot is mounted the camera. So images acquired by this camera are processed. Okay, they are processed, and the information that are extracted from the images are compared with some reference information. We will see this can be of different nature. And based on this error between what we see in the image and what we expect or we want to see, is feed this control law that generates reference position or velocities in the Cartesian space. And then here we have a classical Cartesian controller. Okay, I have a notification, but I think this is an error, so I decline this request. Okay, so I was saying that this is a classical Cartesian controllers that takes as input reference pose for in the Cartesian space, or velocities in the Cartesian space, and computes some. So if these are set point references, there is here also trajectory generation in the joint space, and then here we have joint controls. Okay, this is since the control, the visual servoing control is external to the lower level control of the robot that is realized by this Cartesian controller, and there is, there is also another lower level controller that is closer to the motors, to the control of the actuators manipulator. So this is external for this reason with respect to the other levels of control that are closer and closer to the actuators to the joint actuators, and it is, I mean, for this reason here this kind of control is appropriate for relatively slow situations. So, I mean, a rough estimation is that this can be applied at control sampling frequencies of less than 50 Hertz. This is the frequency, the control frequency of this external control loop. The advantage of this kind of controller is that it is an easy control loop with respect to the robot, because it is essentially the same as that we have without vision. So the external control loop, the visual control loop, is used to provide references to the Cartesian controller. Okay, so it's just an add-on. Different is the case of a direct or a so-called internal visual servoing. So here you see that the scheme is a bit different, because the image, after processing the image and so extracting the information, the current information that we acquire from the camera while the robot is moving, compared with reference information. It is this error that generates the control action, and the control action can be directly either joint torque or joint velocities, reference joint torque and reference joint velocities. And here, as I said before, we have the very low level joint controllers. Because in this scheme, this control scheme, we generate directly commands for the joints. We are actually working at a higher frequency, so it's preferred in a situation in which fast motion or fast reaction is required. So complementing the previous range here, we are talking about frequencies greater than 50 Hertz. So the control law here is a bit more complex, and of course, since we are generating directly commands to the for the joints, we need to include some information about motion of the robot, so kinematics or dynamics. Okay, so but now we can the visual servoing schemes are even can be also of two different kinds, depending on the way we generate the error. Okay, to control our robot, essentially. We have a position-based visual servoing, which is the one on which today we will concentrate, in which the information is extracted, the information extracted from the images, that is the features. Today we will concentrate on the image-based. So in position-based visual servoing, the information extracted, as I was saying, from the images, that is the features, is used to reconstruct a 3D pose of an object, and this, combined with the knowledge of a desired 3D pose, generates a Cartesian pose error, and based on this, control value control command is generated that drives the robot. While in the image-based visual servoing, that today we will see in detail, the error is computed directly in the image plane. Okay, so without going through the 3D reconstruction step. And then the problem is formulated in the image space. So to make the robot move from one pose to the other, we need to connect this desired, this task to what happens in the image space and formulate this task in the image space. That is, we define an error, and through the visual servoing control law, we make this error converge to 0. And if this error in the image plane converges to 0, this should imply that the robot is executing its task. Okay, so it's always, and as we will say also later, this is task control. This control of robots in the task space, except that the task space is a peculiar one. It's depends. I mean, it's a task defined in the sensor space, and this can be, of course, of different nature, as we have seen before. There are also mixed schemes, so-called 2.5D methods that uses that defines the error in the image plane, but uses also some 3D information. They have been introduced mainly to increase the robustness of these methods with respect to uncertainties, okay, of both visual servoing control schemes. So here we see a sketch. This provides a schematization of what happens in position-based visual servoing and the image-based visual servoing, a visual comparison of the two approaches, of the two schemes. So one in PBVS, we have the current image and 3D information that we want. I mean, for the 3D information that's summed to the combined with the current information provides with the current 3D pose of the object, and this current 3D pose of course, in between there are some transformation between the camera frame and the appropriate frame in which the desired 3D pose has been defined for the object, and based on this error, command is generated for the robot. In the image-based visual servoing, instead, we have the current image and the desired one. So you see that here, for example, the two images differ with respect to the magnification with respect to zoom. So here we need to go from here, from this image to this one. What do we need to do, in your opinion? Let me ask you some questions so I see if you are following or not. How many of you? 28. So I expected a bit more, but what do we need to, if this was the image of a camera in your hand, but you would like to see, so this is the current image, but you would like to see this image. Get closer, yeah, very good. Okay, so you see that somehow this is intuitive. Some operation can be explained also intuitively, and so it is exactly based on this error, so comparison between what I would like to see and what I'm seeing now, that I decide what to do. In this case, get closer. Okay, so here we see in a block scheme of the position-based visual servoing architecture. So the robot, and once again with the camera, here we have a high-end configuration. here is the object with some visible features. So most likely, for example, we would like to, if we want to track this object, these 2 points here will represent the features that we will extract in the image processing step, and based on these features will be selected in such a way that 3D reconstruction is possible. So this is quite a difficult step, but in the end we extract from this the pose of the object, so position and orientation, and we compare this with the desired one, and based on the error we have in the end, since we are working in the 3D space, because we are computing the error in the 3D space after this comparison between the desired and the current pose, so the control law is relatively easy. So this method is quite sensitive to camera calibration parameters, because it is based on this feature that we reconstruct the pose, and but then the error, the control, is based on the pose error, not on the error that we see directly on the image. So this is so here we see two examples of application, one with high 2 end or high 2 robot, as said here. So there is on the ceiling, this was our previous laboratory. So on the ceiling there was a camera looking down at this mobile robot, homemade or laboratory made, called Super Mario. So on the top of Super Mario, you see that there are these 3 points that are the features. These three features, because of their geometry, how they are arranged, allow to determine the position and the orientation of the robot in the plane, and the camera, the position and the orientation of the camera and the scene geometry is known, of course. So the task is to move from, so it's a parking task, okay, so a parallel one. The robot should move from here, the configuration that you have seen, to this configuration using the information that comes from the camera. Okay, so based on the position in the image of these 3 points, and based on the configuration of the camera and position, orientation, and geometry, where the camera is positioned with respect to the environment, then it is possible to reconstruct the pose, okay, of position orientation in the plane, in this case, of the robot that we want to control using visual information. Here instead we have a high-end configuration, so the desired pose that we see is superimposed in the on the image plane is the blue one. The target, the object that is detected in the and reconstructed in the image is the green one. And so the manipulator moves in such a way so as to have the two images, the two poses, actually, not the images, because here we are dealing with position-based visual servoing, so as to the two poses coincide. I mean, zero error between the desired and the actual 3D pose of the object. Next, so the other configuration, the other architecture, as said, is the image-based visual servoing architecture, in which, once again, here we have the robot, the object, with the features quite easy to extract from the image. So here there is a, of course, this is an example. In the reality, feature extraction is a quite challenging phase, a quite challenging step in the visual servoing loop, control loop. Anyway, extraction of the features. So these features are usually, denoted as with a vector S. So the current value of these features is compared with the desired one, and based on the error that is defined, remember, in the image plane, okay? Because directly we compare the value of the features, current value of the features, with the desired value of these features. And based on this error, we generate command for the robot, okay? So this implies that this is a control law that is defined with respect to an error. It's a control law that works, takes as input an error defined in the image plane, and produces as output commands for the robot. So inside that, of course, we need to know the motion model, the model of our robot, either kinematics or dynamic. Here, today we will consider essentially kinematic model of the robot. Here, actually, there is one more step. This step is hidden here in this scheme because V and omega, so the output of this block, is the velocity of the camera. Okay, so there is one more step. Here we have the V and omega that are the velocity of the camera, which is in the end of the manipulator. So from the velocity of the camera, we need in the end compute the commands to the joint space. So there are different steps that link the error in the image plane to the error defined in the image plane to the velocity of the camera, and then we need to link this to the velocity of the joint, to the joint velocities. Here we have an example of so the effect. Here we see what we can do with the visual servoing control scheme, an IBVS. So the desired position of these features, of some features in the image plane, is given by the red crosses on the image, defined on the image. And during the motion of the manipulator, this is a 9-end configuration, the features, some features are found out in the images that are the current feature position, and motion based on the error, so current value of the features and desired one, the robot moves so as to let the current feature converge to the desired feature position. Okay, in this case, the features were point. So here we see a comparison between position-based visual servoing and image-based visual servoing. In the first part, so the PBVS reconstructs the instantaneous relative pose, 3D pose of the object. And here is what we see. This is the what the camera sees. So this is the image plane, and we see the motion of the features. So the features are the centers of these four black discs. Here on the right, instead, we have the IBVS. So in this case, the error is defined in the image plane without reconstruction of the 3D pose. So the motion although not identical, is very similar, but in this case, I mean, there are the uncertainties are limited with respect to calibration uncertainties, so both calibration errors in the kinematics of the robot and calibration errors in the camera parameters. This can be, I mean, both the schemes are, show some degree of non-robustness with respect to these uncertainties, and so another methodology that allows to comply with to deal with calibration uncertainties is the 2.5 visual servoing. That is something in between the two approaches. Okay, which are then we have mentioned the necessity of an image processing tools. We have said that we need to specify which is the configuration of the camera with respect to the robot. We need to specify, I mean, we have the choice of choosing the control scheme that we want to adopt. But then let's put all of this together to see which are the main steps in a visual visual servoing control scheme, and in particular in an IBVS, which is the approach on which we will focus. We will concentrate today. So we have image acquisition. So we have a camera, and we need to acquire images from this camera because this is the information that we process to extract the features that are the information, the essential or synthetic information, the information that we need to achieve our control task. Okay. Now, which are the issues related to this image acquisition step? And first of all, the frame rate, because as we will see, there is so the image is acquired by some hardware. Okay, and so there are limitations in how many frames per second we can achieve, how many images of the scene per second we can achieve, and then elaborate to compute real-time commands. So this is an issue because depending on the vision system, sometimes I mean there are some upper bound, of course, on this frame rate. In principle, as for other sensory information, the higher the rate, the better. I mean, the faster we react to what is happening in the environment. We always, assume that the control rate, the control frequency. When I say the higher the rate, always compared to the control frequency, of course. So with respect to the control frequency, the higher the rate of sensor information acquisition, the faster we are in reacting. I'll say this is often, in vision system, this is often a challenge because we cannot achieve, for cheap sensors, we cannot achieve very high acquisition rate. Just to provide you an example for the robots that we have in the laboratory for a small humanoid robot now, that nominally the frame rate for the camera that is mounted on now is 30 Hertz, but in practice what we could achieve at maximum was 10 Hertz. Why? Because the frame rate is also affected by other operations that are executed in parallel to the vision, to the image acquisition process. Okay, so frame rate could be an issue, is something that we should take care of when designing visual servoing control scheme. Another issue is delay in the transmitting the information. This is particularly true for mobile robots, and often, for example, it is depending on the computational power that is on board the robot. Sometimes, because the image processing step is quite expensive in terms of computational resources, it is performed on a remote computer, and then there is some delay in transmitting the image, and then based on the images, transmitting back commands to the robot. And last but not least, and this is a very big issue, is noise. Images are noisy. There is no way to get rid of this, and we have to deal with noise. We need to filter this, and depending on the quality of the sensor, on the nature of the scene, noise is a real problem. And in the medical domain, as we will see, we will comment on, for example, on Monday, processing the images of an endoscopic camera is a real mess. Okay, so once we have acquired an image, there is the step of feature extraction, because as said, we need to extract the basic and not the basic, the information needed to achieve our control task. This is done with imaging processing techniques, and as already said, can be a time-consuming and also computational resources consuming step. Once we have these features, we compare them with desired values, and we compute the error in the image plane, and then based on this error, we need to generate the motion of the camera, or the motion of the robot, or of the camera and the robot, because in the eye-in-hand configuration, by generating the motion of the camera, we are generating the motion of the robot, because it is the robot that moves the camera. Okay, so we need to because the objective, the task, is defined in the image space, then we want this feature to change values, like in the example before, that what we have seen, that we want to see a bigger image of Lena, that is a famous Lena. We want to see a bigger image of Lena, and then we need to move closer, right? So we want the features to move in a desired way on the image. How do we move the robot or the camera in such a way that the features move as desired? So we need to link these two dynamics, the features and the robot. And in doing this, of course, we need to map information from one space to the other. Then we will use perspective transformations, model of the manipulator, use kinematic model, and then the control law that in general can be of kinematic or dynamic type. Today we will see mainly kinematic control law. The image processing technique, as said before, can be binarization. GAUSS. This is the simplest image processing that we can procedure that we can perform goes from then binarization that can happen either in a RGB space or another in color space, parameterized in a different way as a HSV, and then after binarization, we can further refine the image that we obtain through operation of erosion and the dilation of the image that we have obtained after binarization. Erosion essentially is useful to clean the image from this noise, this pixel here, while dilation is useful to fill the holes that can become after the erosion. So this is what we obtain here. Binarization is done through a simple thresholding operator. So looking for the for pixel with the green color, characterized by green color. Now here. Okay, once we have processed this image, we look for the features, because in the end we need to find specific information in the image. So what is a feature? The feature is, any can be defined in different way depending on our task, but in general is any interesting characteristic or geometric structure that can be extracted from the image. So for example, the simplest feature that you can imagine is and it is often used are points. But of course also lines or ellipses or any other 2D contour. Okay, associated to features, there are numerical quantities that are the quantity that we actually use in the control law. For example, for a point, we do have the coordinates, or for a line, the angular coefficients and the offset, or the center and radius of a circle. More in general, we can compute the control law based on the image moments. Image moments characterize some statistical properties of an image. For example, the area in the center of a 2D contour, of which, if we use moments, we don't need to to represent geometrically the contour. We will see later the area and the center, the coordinates, for example, barycenter of a given segment in the image are examples of simplest examples of moments. So in principle, this is a powerful way to control the motion of the robot based on the visual information, but has some drawbacks for the difficulties that there are in controlling all the 6 degrees of freedom of the camera, although some results exist in particular cases. Now, but now all that said, so we concentrate on features. Okay, we have a complex information provided by vision, but we concentrate on special quantities that we call features, and actually to the quantitative, to the values associated to these features that we extract from images. But now, once again, we need to link the motion of these features in the image plane to the motion of the robot. And then for this, we need a model. We need a model of how these features are generated by the sensor. I mean, how they, how the image is formed on the image on the sensor in the sensor space, and then based on this, how the features are provided by the sensor. We will derive a very simple geometric model of a camera. Here we remember, I mean, in general, you have studied this in the Robotics 1 course. I think you studied this also in visual perception, and you know that there is in a camera there is an optical component that is used. The optics that that focuses the incoming light on a matrix of light-sensitive elements that are possibly selective with respect to the colors. And then a frame grabber takes like shots of this matrix. Can be they can be the frames can be generated by an analog signal as the output from an analog signals or from digital video stream. In any case, we do have this matrix of points, the pixels, that provide information about the scene. Because it depends on how the light reflected by objects has been focused and has been generating the response of these points of the pixel, of the sensitive elements on the sensor matrix. Okay, so how this happens geometrically? So we adopt the thin lens camera model to see how the light that is reflected by an object is focused through the thin lens camera, so as to generate, an image on the sensor sensitive matrix. Now, here, to simplify, consider a point in the workspace, a point P, and the lights. Now, how the lights that are come from this point are focused by the lens on the image plane. And here, the geometry, the thin lens camera model says that the rays parallel to the optical axis, like this one, are deflected through a point at a distance lambda, which is called the focal length, while the rays passing through the optical center are not deflected at all. So this point P will generate this image on the image plane. Okay, and this is, there is also the symmetric focusing of the ray that goes through the point at distance lambda from the optical center that then is deflected in parallel way to the optical axis. Now, using this geometric construction, it is possible to find out the fundamental equation of a thin lens. How do you find this? This is left as an exercise. I can only suggest to use similar triangles. So this one, for example, PZO and OZ, small z and x, and then these other two, lambda, the image of x on the lens, and O, and the bigger one, P, image of x on lens, and O. So using this similarity, you will be, between triangles, we'll be able to find this relationship, this fundamental equation of a thin lens. But this is not yet the model that we will use. Because the other approximation that will be used is that of the model so-called Pinhole camera model. Pinhole camera model, in which that imagine that the the width of the element of the lens is actually reduced to a point. So we will have only the ray going through the optical center, and also assuming that the little z, the big Z is much bigger than the little one, we will obtain that Z, this point here, is actually approximately equal to the focal distance. So using this approximation and also changing the position just for the sake of derivation of the mathematical model, because this avoids some sign changes. So if you see here, we have the image is that you see on the image plane is upside down, so there is a change of sign in the equation in the coordinates. To avoid this, then we take the image plane from the back of the lens and we put it before, so that the optical center is behind the image plane, and the image plane is placed at a distance lambda from the optical center. That is exactly the focal length. So with this approximated construction, the image of a point P in the Cartesian space with coordinates x, y, and z is the small p. The small p that with coordinates u, v, and lambda, the focal. So the image. Now here again, using similarities, we can compute the coordinates of the point P as a function of the coordinates of big P, so in the Cartesian space, and of the focal length lambda. Okay. Now this is actually here some other details are neglected to keep the derivation simple, but to obtain this from discrete pixel values, there is also an offset and the scaling factor that should be added in each direction. Well, we do not consider this in the following computation. Okay, now that said, we have found the relationship between coordinates in the Cartesian space and coordinates in the image plane. Now we illustrate here which are the reference frame of interest, and then we will put in relationship the derivatives of the coordinate on the image plane and the velocity of the camera. But we need first to specify which are the reference frames that are, used in this derivation. On one side, we have here the image. Well, first of all, let's follow this list. We have an absolute reference frame that we call FO. We have a camera reference frame, FC, that is usually placed in this way with the Z direction, the Z direction aligned with the optical axis and going through the origin of the image plane reference. And we, to go from, there is a transformation, of course, from the camera frame to the absolute reference frame that, as usual, is specified by, it's a rigid transformation, so we have a roto translation. Okay, so that said, given we need now, finally, so what time is it? Yeah, we still have some time. We need now to link velocity of the features in the image plane to velocity of the camera. That's what we will do now. So given a set of features, parameters, as again we need quantities, right? So the value of some parameters. So we put all together this features parameter in a vector of that we call f, and we will look for the kinematic relation, the differential relationship between the motion imposed by the camera and the motion of the features in the image plane, as already said. So we need a relationship of this kind. On one side, the derivative with respect to time of the featured parameters, that is, how do they change in time, depending on the velocity of the camera. So we need to find out this matrix J. Okay, so V and omega is the camera linear and angular velocity, that is a vector expressed in Fc, in the reference frame of the camera. Okay, J is called is a k by 6 matrix and is known as the interaction matrix. And now we will find the this interaction matrix for a point feature first, and then we will use this to find interaction matrix for also for a couple of other kind of features. But there is a general way also to find. Okay, I'll say it later in more general cases how to proceed. Okay, so from the perspective equations that we have found, considering the Pinhole camera model, we know that u and v, the coordinates on the features of a point feature in the image plane, are related to the coordinates of x, y, and z of a point in the Cartesian space through these two equations. Then we take the time derivative of u and v. Take the time derivative of u and we will find which is the relationship between the velocities, the derivative of u and v in the image plane, and the derivative of the point x, y, z in the Cartesian space, right? They depend on this matrix that we call J1, that is a function of u, v, and lambda, so the coordinates of the feature in the image plane and lambda, and also I mean, we will comment on this. You see that every value here, every quantity, I'm hearing background noise. Okay, I was saying that we take the time derivatives of u and v, and we find out the relationship with the time derivatives of the coordinates of the point in the Cartesian space x, y, and z. Remember that x, y, and z are the coordinates of a point P in the camera frame. This is important. So here we have the velocity of the point P in Fc. But this velocity, actually the point is considered as fixed in the fixed frame in F0, okay? And then the velocity of this point, to find out the relationship, to find out the interaction matrix, we assume that P is fixed, and the velocity of this point is only due to the motion of the camera, okay? And the kinematic relationship, it's a basic kinematic law between the velocity of the point P and the velocity v omega of the camera, is due to the linear velocity of the camera, and the rotation, is generated this velocity relative, okay, between the point and the camera, is due to the translational velocity of the camera and the rotational motion of the camera as well. Okay, so this is a classical kinematic relationship, and we use this relationship between the velocity of P in the camera frame we use that relationship to find out, to finally find the relationship between the velocities of the features in the image plane and the velocity v and omega of the camera. So we have found that we have written the relationship between the velocity of p in the camera frame and the camera velocities in this way. We rewrite this in this way. And then finally, so you can also, in a compact way, this is another matrix J2, function of x, y, and z, the coordinates of the point P, then combining the expression of u and v dot with what we have found here for the derivatives of the coordinate of the point P in the camera frame, we finally obtain the interaction matrix for a point feature, okay? Because here we have substituted to x, y, and z dot this expression, and then finally we obtain, the velocity of u and v in the image plane as a function generated by the velocity v and omega of the camera. Okay, so the interaction matrix takes on this expression that, as you can see, is a function of the coordinates u and v of the point in the image plane and of the depth z, the depth z of the point in the Cartesian space, expressed in the camera frame. Remember, well, assuming that lambda, the focal length, is known, this is obtained. This is either provided by the constructor, but can be obtained also, through calibration procedure. Sorry, I missed the word. So here you see the dependence of this interaction matrix only on the variables of our problem, u, v, and z. Okay, so we now have the relationship that we were looking for between the dynamics of the features and the velocity of, the derivative of the features and the velocity of the camera, and this expresses dynamics of the features. Now, how is this? Let's analyze the structure of this interaction matrix. Interaction matrix, in this case, for a point feature, is a 2 by 6 matrix. So the dimension of the kernel of the null space of this matrix is equal to 4. So this means that there exists infinite at the power 4 motions of the camera that are not observable for this feature. So, for example, if I'm looking at a feature that is exactly, at the center of the image plane, if I use a camera, right, like my telephone, and I move along the optical axis or along the projection ray, the simplest projection ray is the optical axis, I'll not see any motion of the feature in the image plane. Okay, so there are some motions that are not observable with this feature, and that is why if you want to control all the motion, the 60 degrees of freedom, motion of the camera, one feature is not enough. Okay, because there are some motion in the null space of this interaction matrix. Now. So very often we use more point features, and the associated interaction matrices are stacked one on top of the other. We will see some examples. So if P is a point feature, the interaction matrix is a K by 6 matrix, where K is equal to P. Okay, because if we the parameters associated to the feature point are the two coordinates of this point. Okay, so for example, here we have as a feature, we can choose the distance between 2 point features, so one with coordinate u1, v1, and the other with coordinates u2, v2. The distance is the Cartesian distance. We take the time derivative of this, and we will obtain that it depends on the time derivative of u and v1 and uv2, so the coordinates of the 2 points. So since we do know which is the interaction matrix for a point feature, we put things together and then we will obtain the interaction matrix for the distance again. So the derivative of t as a function of the camera velocities. More in general, we can use to define feature the image moments that we have already cited before. So if we consider here R of t as the region of the image plane that is occupied by the object, by the object image, okay? So, and we want to characterize we want to associate to this region some feature, so some property, statistical, as defined by moments. The mathematical expression defining the moments is this one that we can easily interpret geometrically in case, for example, I and j, so the moments, the order of moments are defined by the value of I and j, okay, that are the power of the coordinates of the point in the image plane. So if I and j are equal to 0, then M00 is the area, okay, defines the area of the object. If, on the contrary, one I and j either I is equal to 1 and j is equal to 0, or I is equal to 0 and j is equal to 1, then we find the center, okay, of the center of gravity of a given region. Okay, so the image moments, are not new, have not been invented within the theory of visual servoing. They exist much before. Have been widely used in computer vision. The point was, the difficulty was to use this very interesting concept in visual servoing, because we need to characterize, to use this information to control the robot. We need to find out the interaction matrix that we have found now for a point feature. Was quite simple to find for a point feature. So they have not been used extensively until in 2004. So not in relatively recent years, by François Chaumet, who characterized analytically the interaction matrix for use for image moments. Okay, there is this interesting, and then starting from the using the interaction matrix of a generic point feature. And this is the reference paper, a very interesting reading if you are, want to deepen your knowledge in the visual servoing. Here we see again from François Chaumet, image-based visual servoing with straight lines, for example, using straight line as features. So you see the effect of the motion of the robot, that are a consequence of the motion of the object, but only using errors defined in the image space. Okay, let's move forward because now we want to know. So till now we have found. So can give me just 1 minute because I need. It's me now to hear some noise. So I'm going to close some doors. Sorry, 1 minute. Okay, here I am again. Well, what I was saying that yes, till now we have found we have expressed the dynamics of the features generated. I mean, the function of the camera velocity. Now we want to see how the camera, I mean, which is the link we want to link the camera motion to the manipulator joint motion. Okay, so the case that we analyze is the INAND case, similar computation, analogous computation needs to be done in the eye-to-end case. So in the eye-to-end case, the camera is mounted, as we have said, on the end effector of the manipulator. Doesn't matter if the manipulator has a fixed or a mobile base. And the velocity v and omega of the camera is realized by the joint, manipulator joint velocities. And then it's easy, and you know very well this, for a manipulator with a fixed base, fully actuated, you know that the geometric Jacobian relates joint velocities to end effector velocities that we assume the end effector is where the camera is mounted in this model. Of course, if you have offset, you need to take into account this with respect if you have the gripper on one part, on one side, and the camera, you know, mounted with some offset with respect to the gripper, and you want to do operation as in the first video that we have seen, you need to take this offset into account. In any case, you know how to do this, right? Relate joint velocities to end effector velocities. In our case, end effector is the camera. Okay. Now, it is also possible the same, I mean, to use the same kind of mapping between velocities, even though, for example, we do have some constraints on the some velocity constraints at the manipulator side. For example, in the for a fixed base manipulator fully actuated, the inputs are the we can assume that the inputs are the joint velocities. If you have a mobile base, you know that the inputs, the control inputs, are not the derivatives of the generalized coordinates, right? So here, instead of having derivatives of the generalized coordinates, here we have the velocity control input, okay? So this is general, I mean, it is generally possible, again, to link the camera velocities to the velocity commands of a robot, okay? Once we have done this, well, we just need to put things together, combine things together, and going back to the dynamics, to the time derivative of the features, we have seen that f dot was related to the camera velocity through this interaction matrix, but the camera velocities can be expressed. The camera velocity is given by the manipulator Jacobian times the with the input the velocity commands of the manipulator. Then we combine things together, and we can express in a compact way the dynamics or time derivative of the features as a function of the velocity input of our robotic system time this matrix that is called the image Jacobian, that actually is the product of the interaction matrix with the manipulator Jacobian, and plays the role of a manipulator, classical manipulator Jacobian. It maps control inputs to the manipulator to task velocities. Okay, in this sense. So in here we have already said this. Okay, so now we need, based now that we have the model, we have the control inputs, and we have the output that we want to control, that are the features. We need to design. We need to find the control law, to define the control law. Okay, so first of all, we define the error, and the error is the difference between the desired value of the features and the current actual value of the feature f. Then we can using kinematic control that you have studied a couple of lectures ago in the Robotics 1 course. So using kinematic control, a general choice for the control input is as follows. So here we have the pseudo-inverse that provides a minimum norm solution to achieve the desired task. And this is classical. This term here is provides asymptotic stability for the error dynamics, so guarantees that the error converges asymptotically and exponentially to zero. Since most of the time these the manipulator is redundant with respect to the task that has to be executed, we do have some null space, and then we can project some velocities in this null space. So these velocities are projected in a null space are robot motions that do not move the features. So the current meaning of self-motion. But in this case, the self-motion are internal motion of the manipulator that do not affect the motion of the features. Okay, so this auxiliary vector U0 can be used for optimizing to achieve additional tasks. Now, the error feedback, as said, depends only on the features values. Okay, this error is defined as the on the image plane, depends only on the features value, but there is still a dependence of J on the depth Z of the features, and this is because we have a projection of a 3D scene on a 2D plane. We lose this information of depth as well known, and this is one of the challenges. One of the things that should be managed in implementing image-based visual servoing scheme. Sometimes, I mean, actually the control is quite robust with respect to uncertainty of the depth. It has been shown that one can use constant unknown values at the desired final pose, or if we want to be extremely, I mean, if we want to be more accurate in the control, particularly in the transient phase, estimate online the value of the depth. And now we provide some examples of application of visual servoing here for a non-autonomic mobile manipulator. That is, here we have a base. This is a Magellan. This is a model, a 3D model of mobile robot called Magellan that we do have actually in the robotics laboratory. So on the top, this is a simulation model. So on the top of the mobile base, we have a 3R manipulator mounted, and at the end effector of the manipulator there is a camera. So we have an eye-end configuration. Okay. Overall, we do have 5 commands. Okay, because for the mobile base we have linear velocity and so driving and steering velocity. So how to advance and how to turn the mobile base, and 3 plus 3 joint velocities for the manipulator. If we specify the task by 2 point features, then we have 4 output variables because we have 2 coordinates for each feature. Then we do have 1 degree of redundancy because we have 5 commands and 4 output variables to control. Okay. Here we see, so the the task defined in the image space is to take these 2 features that are the simulation environment that we don't use any longer, was called Webots, but it is similar to VREP that you probably know. So here, the object is this cube here, and the 2 features are the red spots. Okay, again. The task is to take the image of those 2 features in this position on the image plane. So the green points indicate the position, the desired position in the image plane. Here the value of Z is supposed to be known. The gain, the task gain matrix, I mean here, if you see, I did not comment previously, sorry, K is a gain, and that, for example, as done in this case, can be a diagonal matrix, so as to, in this way, decoupling is obtained in the in taking the error on the image plane to 0 for each of the 2 features. Okay, so, and in fact, in the image plane, we do have a linear path of the feature. Okay. And this is what the robot does to accomplish, to execute the task defined in the image plane. Now, we say that we can, I mean, we have some degrees of the redundancy. We can have more than 1 task defined in the image space. We can, take different approaches to execute our control. For example, For example, execute tasks. You have studied this in kinematic control according to a sequence. Okay, so the approach is to regulate only one of some, so two or more feature at a time, while keeping fixed the others, using only the unobservable motions in the image plane. I mean, those motions that do not move the first feature. So here, for example, taking as example two features. Okay, so the first feature is characterized by this dynamics. Okay, with this image Jacobian J1, and the second feature F2 has these other dynamics characterized by J2, right? So the first feature is we can adopt the general kinematic control scheme to regulate the first feature, okay? And to do this, we use this control law, okay? The general one that has been declined to the case of regulation of the feature F1. And so here we do have some, there is a null space in which we can project some motion or not. But there is a null space of this Jacobian J1, image Jacobian J1. Then to move feature 2 and to regulate him, to take it to the desired value, we use commands in the null space of the first image Jacobian. That is, we choose commands U that take the second feature to its desired value. Okay, this is, and this part here, but it is projected in the null space of the first feature. Okay, so in the first phase there are, of course, 2 or more degrees of redundancy with respect to the first case that is here, that even can be possibly use these degrees of freedom to improve the alignment, for example, of the robot with the target or whatever other behavior or task we would like to achieve. Why do we use this? Because if the complete case is not redundant, then we may incur in singularities. Typically, we will incur in singularities, and with this can be possibly prevented using task sequencing. Here we see what is the robot behavior using task sequencing control scheme. So first, the robot. What happens? Okay. So the second phase is so here we have convergence of the first one to the desired value. And then there is a switching point. So the second one is almost aligned, but not really yet. And then we have convergence of the second one. Here again, we have that the depth is known. This is a simulation, so depth can be assumed to be known. Here we have the experimental validation of this approach. So here we have task priority and task sequencing, the two kinematic control modality that you have already studied in the robotics. So here we have task priority, one is projected, one task is projected in the null space of the other. Here we have the sequencing. So here clearly first this feature is regulated to 0, and then the second one almost, of course it's very noisy. The experiments are always different from simulation. And then the second one. Okay, so here the camera frame, as you can see, is very low, is 7 Hz, and this is one of the difficulties, I mean, on the visual servoing, because it is also a quite old model of camera. As said, even with an our robot today, that is a very cheap robot, we can achieve real 10 Hertz. Well, in many practical cases, what happens, I've mentioned at the beginning the robustness with respect to calibration uncertainties, and this actually affects the perfect knowledge of the image Jacobian. So, for example, which are the parameters that we might not know with appropriate accuracy. So the focal length, which is which is an intrinsic camera parameter. Also, and eye calibration, that is where the camera is mounted on the robot. This is another parameter that, of course, affects the perfect knowledge of the image Jacobian, because in computing the image Jacobian, we need to know where the camera is on the manipulator. And this is an extrinsic camera parameters. Also, the depth of the feature, that is an unknown. I mean, it's a variable of the problem that we do not know. We will see in the following slides that there are algorithms, that are methods to estimate this. For the intrinsic and extrinsic camera, and extrinsic camera parameters, there are methods for calibration, okay? But in any case, if either to take into account, I mean, the non-perfect or properly high accuracy in the knowledge of these parameters, even after calibration, or in some cases, we actually cannot know the image Jacobian because of the both because of the interaction metrics part and the robot Jacobian part. In the medical application, we will see that most of the time it is not possible to obtain an analytic interaction matrix, and then it is estimated. It is estimated, and then we do not know it, with infinite accuracy or with the appropriate accuracy. So we only have an estimation of the image Jacobian, and we denote it with a J hat, this estimation. Now, if you use this approximate image Jacobian in the control law, then the closed loop dynamics of the error is like this. So in principle, in the ideal case, you would have that if this J hat transpose will be J transpose, of course you would have here the identity, and then you will have a linear, syntactically stable dynamics for the error. But in the general case and in the real case, and when you are in a situation in which the interaction matrix cannot be known analytically and with high accuracy, then this will be in general different from the identity matrix. Then how can you prove convergence of the visual servoing control scheme, where there are some results in the literature, actually sufficient condition, only sufficient conditions for local convergence of the error to zero. And this sufficient condition is that the product J transpose hat should be definite positive. Okay, so if this can be satisfied, then we can guarantee local convergence. Okay, so here we see again by François Chaumet, who is a French researcher that are given significant and numerous contribution to the field, to the theory. Here, first we use in this video the J is supposed to be known, while here we have an estimate of the Jacobian, so that is computed at the fixed depth Z star. And here is, you see that both converge asymptotically to 0, but the trajectories are different, particularly in the transient. So here and here, you see? Okay, so what can we do with the depth? What can we do with the depth? How? So we have said we can use, and this is shown here, we can use the depth at the target, like in this case, and then locally we can still guarantee convergence, or we can devise an observer, like is in the example that I will show now, an observer that estimates the depth. Okay, so nonlinear observer has been constructed. Define first the state x, the state of the observer given by u, v, and 1 over z, and x hat is the estimate of the state, while the output y that is provided by the image coordinates u and v is the measured output. Okay, so using the measured output and the commands of the camera, so you see the command is the velocity of the camera, then you can construct a nonlinear observer and guarantee that the error goes to 0, provided that these conditions are met, that our linear velocity of the camera is not 0 and the linear velocity vector is not aligned with the projection ray of the considered point feature, because otherwise we will not see anything, we will not see any motion of the feature on the image space. That is, these two are persistent excitation conditions that are conditions for observability. Okay, so which is the structure, which is the scheme, the block diagram of this observer. Still, we do have here so the camera system. Okay, that's given some velocity of the camera, we do have some values of the features, right? So we send as input to the observer the velocity of the camera and also the error, as usual in the observer schemes, and then we have an estimate of the features value. Okay, and the estimation error is given exactly by the difference between the current features and the current value of the features and feature parameters and the estimate. And here we have the results in the estimation of Z. So here we have the estimation errors, E1, 2, and 3, that is the difference between the three coordinates, and the first two coordinates start on the same value, so with 0 error, while the Z is a different one. Okay, it's the value that we want we want to estimate. And now here we have, okay, the evolution of Z. In blue we have the true Z, and in red the estimation of Z. And so you see the convergence of the Z to the real value. Okay, so this, of course, these commands respect the persistent excitation conditions. And here you see a video that shows in an effective, very effective way, I think, the evolution of the observer, of the estimation of the depth of a point using some exciting commands to the input to the camera motion. So the red cross here represents the estimate, the value of the depth as estimated by the observer. You see that at the beginning, so it's a quite fast convergence. At the beginning, the red cross is actually initialized to be coincident with the, close to the camera, and then it's rapidly converged to its value. So how do we use this observer in a IBVS control scheme? Well, it is, I think, quite obvious for you now, because we know that so the external control loop is the usual one in IBVS, that is based on the error. So here is the feature extraction step. Based on the error defined in the image plane, that is the IBVS control law that provides the desired velocity of the camera, and then, as we have seen, this velocity of the camera, desired velocity of the camera, is transformed in maps to commands to the joint, to the robot joints, right? Now, here in this IBVS control law, since we are using the image Jacobian depends on, via the interaction matrix, depends on Z, on the depth. We have seen that it is possible to use a fixed value for the Z, but if we do have an estimation, so to be more robust with respect to convergence of the image error, we can inject here, we can use the estimated value of the depth, the value estimated through the nonlinear observer that we have just mentioned. Okay, so it's quite seamless, the insertion of this estimator, this observer, within the image-based visual servoing control scheme. Well, here there are some experiments performed in Siena, I think, a few years ago by Paolo Robuffo Giordano, and the example, the system is given by this mobile robot, skid steering mobile robot, on the top of which a camera has been mounted. So it's a eye in-hand configuration. A very rough eye robot calibration has been performed. So, the interaction, the image Jacobian is known with some approximation. Okay, so we have the J hat rather than the J. And then also the depth of the target point is unknown and are unknown and are estimated online. Okay, so this is the target is represented by this picture. So 4 points are the features on a plane, and there is also a 5th virtual feature that is used as the average of the point feature. Okay, so it's not present really physically there, but is used in the control. Okay. So the motion of the features on the image plane, as we will see also in the following slide, is not perfect, but the regulation task is achieved, is realized, is executed. We see the 4 desired green points that converge to the red points that are the actual position of the 4 features in the image plane. Okay. And here is what we obtain. I mean, these are the real experimental value of the features trajectories in the image plane. Okay, you see that toward the end the motion is almost linear. Okay, so here we have a transient, and then the convergence is almost linear because the depth observer, this coincides with the convergence of the depth observer to the true values. So here we have an estimate as the the estimate of Z converges to the real value. Also the estimate of the image Jacobian converges to the real one. Okay, so here we have that the true initial and the value of the true initial and final depths. And in this plot, we have the evolution of the depth in 5 different experiments with different initialization. And for all of these experiments, there is convergence of the depth to the true final value that is around 0.9 meters. Okay. Okay, here we will see now some experiments with depth, so visual servoing with depth estimation with the Kuka robot, the Kuka manipulator KR56 that is in our robotics laboratory, that has 6 revolute joints and a spherical wrist. A point gray camera has been mounted, a CCD camera on the end effector of the robot, so it is a 9-end configuration. The image processing is performed on PC, and the control data are exchanged at 12 milliseconds. Okay, so these are details of the implementation of this visual servoing at a quite high rate. So first the simulation, and here you see that there is a first phase. A first phase in which there is this sinusoidal motion of the robot that is used to provide the sufficient excitation that is needed for depth estimation. Okay, and then once the estimation converges, estimation of the depth converges to the real value, then the error in the image plane is driven to 0, okay, through visual servoing. So we will see this. Okay, so here, and this corresponds to this last part in the plots. Okay, and here the corresponding, so this was the model of the Kuka robot, and here we see the experiments with the same robot. Okay, in this experiment, beside the estimation of the depth there is also some additional challenge that is due to the motion of the target. Now, the target needs to move slowly because, as said before, this is a disturbance with respect to the visual control scheme, since the target is assumed to be static, to be still when we derive and that the motion of the point feature is only due to the motion of the camera. Okay. And one more example is servoing of a humanoid ant. In this case, stereo vision is present, and there are 7 joints, but only 6 degrees of freedom are independently controlled. The visual task dimension is equal to 2, so we have enough redundancy that is used to keep a better posture and of the head and to avoid joint limits, and this is obtained by projecting some additional velocities in the null space, but also there is a predictive feed forward that is used for faster reaction following of the moving target. Okay, that's the okay. Okay, so you see that here the motion is quite fast, and this is due to some predictive feed-forward term. Okay. Okay, there are also, some differences here. We see the final posture that you have without and with self motions. That is, if you do self motions, you can obtain final posture of the head that is better, consider a better posture, and here you see the 2 examples. In one case, the head after following and because it is redundant, even though you make a cyclic motion in the roughly in this case because it was moved manually, but even though you go back and forth in the image space internally, you can have some drift in the degrees of freedom, and so you can end up with a posture of the head that is not natural, because you start straight and then you end by leaning, and you can use redundancy to constrain the internal degrees of freedom. Okay, so we have completed. Okay. So we have a message from Professor De Luca. I think that we do not have the time. I would have liked to show you some more examples, but I think it's better to stop here. Please remind the students where they will find the recorded video lecture in the Robotics 2 playlist. Okay, so sorry. Remember that, so now it will take some time to get the recording of this lecture. Well, in a couple of days you will find the recordings in the Robotics 2 playlist, in the video DIAG channel, and of course in the e-learning environment for medical robotics. Okay, so I think we stop here, and okay, if you have questions, of course I'm happy to take your questions, because we have a few more minutes, but I would not add much more to what's already said. Okay? So if you have questions, please ask. This is I stop recording, so your questions will not be recorded. And if you do not have questions, please tell me